Hi, welcome back. So sorry that there is no video for the past few days because I was busy for something else. So let's go back to the uploading schedule. Last week I mentioned that for the mathematical methods, I will stop at y equals to cos x for the moment, and then we will derive the product rule, quotient rule, chain rule before we go into other functions. So let's go into the product rule first. So let's assume that your y is ux multiplied with bx. So the derivation of this will be given by this particular limit by first principle. So at this point we try to add one term and then minus one term. Is similar to you plus 2 and then minus 2, it cancels out. So which is why there is no problem if we do that. So here I choose minus ux multiplied with vx plus h and then plus ux multiplied with vx plus h minus ux vx. So it's quite easy to see the reason why I do that, because essentially I want to break down this particular limit into two parts. So the first part will consist of this particular limit, whereby it is ux plus h minus ux divided by h, and this whole thing you multiply with vx plus h. The second part of the limit, so I know that I can factorize out ux because it doesn't contain h. So this is just vx plus h minus vx divided by h. So the thing is, when your h approaches 0, your vx plus h is actually just vx. So the first part of the definition, the limit when h approaches 0, ux plus h minus ux divided by h, that will be u prime of x multiplied with vx plus ux. The second part is a definition of a derivation, v prime x. So that's how you get your product rule. So part 5, chain rule. So what we can do is to let y equals to u, and then inside there is vx. Okay, so if we try to differentiate this by first principle, what we would get is u v x plus h minus u v x, and then divide by h. So over here, what we are going to do is to let, for example, vx equals to okay, here it doesn't really quite works, because the thing is, you will need to assume certain things. You will need to assume that your Vx plus h is approximately Vx plus a small change in y. So this is the thing that you need to assume if you use this particular definition. There is another definition of the limits, whereby you consider instead x approaches a, and then you have this. So this is another definition of first principle, but I'm not using this. So let's assume that this stays true for some, usually the function that we are going to study, they sort of satisfy up to the first order of this equation. Okay, so if you let Vx equals to y, for instance, then Vx plus h would be something like y plus let's put this g. So if we assume this, what we will have is we successfully change this into a multiplication, whereby this is your u y plus g minus u y divided by, so over here h I changed to something else. I changed to y plus g minus y, so it just becomes g. And then over here I would have, so what is y plus g? Y plus g is basically this. This will be, sorry, x. Then the other side, you will have Vx plus h minus Vx divided by h. So by right, you don't really need to convert this, but it sort of helps you to see why I can break it down in this case, because it is just like a fraction kind of thing. So on the left side, of course we know for sure that on the left side, if you don't want to depend on g, you can rewrite the equation. So it's basically this. So the reason why I do the conversion is to help you see that this fraction actually works. So now that you see that it actually works, I will just write down the original equation without changing anything. So after that, evaluate the limit. So the first part will be u prime Vx, and then you differentiate v. So that is your chain rule. The reason why it is the case is also easy to see, because this particular limit when you evaluate with this gives you u prime vx, whereas this part will give you v prime x. So that's how you see this. So after you have chain rule, you can derive quotient rule by a combination of your chain rule and your product rule. So quotient rule, your function is usually defined to be like this: y equals to ux divided by vx. Of course, you can use first principle to do it, but what I would do is to use the idea of product rule plus with chain rule. So this is just ux vx to the power of minus 1, and we can definitely differentiate that using product rule and chain rule. So the idea of product rule is that you need to differentiate the first one, keeping the second one constant. So you have u prime x vx to the power of minus 1, and then plus ux. So now you need to differentiate the second part, that you need to use chain rule. So you have minus 1, then vx power minus 2, this is chain rule, then v prime x. So now try to put everything back to the fraction form. So you have u prime x divided by vx minus ux v prime x divided by vx square. So put it back, you get u prime x vx minus ux v prime x divided by vx square. So this is your quotient rule. Now that you have all the necessary ingredients, we can continue on with y equals to tangent x, and we know that this is sine x divided by cos x. So we can just apply quotient rule. So quotient rule states that you keep the denominator, differentiate the numerator, minus keeping the numerator the same, and then differentiate the denominator, which is minus sine x. Then you need to square the denominator. So on top you have cos square x plus sine square x, which is why it is equals to 1 over cos square x. So that's the derivation for y equals to tangent x. Now let's look at y equals to ex. Initially we start with base a is positive. So by first principle, you will have something like this. So that will be, okay, let's write down the definition first. Actually we don't need it. So you will have something like this. So you can factorize out a to the power of x, and then you have this particular limit. So the thing is, when we perform differentiation, we always want to define this to be equals to 1. Because when this is equals to 1, the derivation is very simple. We can't really evaluate this particular limit. So what we will do instead is to set this particular limit equals to 1, and it happens when your a is equals to the Euler's number e. So therefore, when y equals to e to the power of x, when you differentiate this, it gives you the same thing. So before I go into the last derivation of ln x, let's introduce something that you will not study in this particular syllabus, but it's incredibly useful, called the implicit differentiation. So implicit differentiation is very useful when you try to differentiate implicit functions. So like functions, for instance, this is not implicit functions, but if let's say you have y squared plus 2xy equals to 0, I should add some x squared term. If let's say you have a function like this, you can't really write y in terms of x, like the first equation. So this is what we call as implicit function. And there is a way for us to differentiate implicit functions called the implicit differentiation. Basically, it's just that you differentiate the whole equation with respect to x and then with respect to y. And that's it. So I will not talk much on how you would perform implicit differentiation, but I want to focus on this. So okay, you let f of x equals to y, then the inverse of y will be given by x. So we take note that the inverse function here in this case is defined in terms of y, because so usually when we do this, at the very end we take note of y equals to x, then we can exchange the label. But in this case we don't do that, because we want to make use of this particular property. We know that the inverse function composite with the original function, it will give us x, right? So we also already define f of x is equals to y, so we need to remember that. So here we can use chain rule. So chain rule dictates that we need to differentiate term by term. So on the left side, when you perform implicit differentiation, you do need to use chain rule. So when you differentiate your f inverse, that will be in terms of y, because your f inverse is a function of y. It's not a function of x. So then we have something like, okay, perhaps I write it. So you have df inverse y of dy. So y, I change it to y here because f of x is essentially y. And then based on this particular equation, you also need to differentiate the inside. Okay, let me write this down clearly. So you will have f of inverse fx, and if you wonder what would be the argument over here, it will be dy, because f of x is equals to y. That is from our definition. So the chain rule dictates that you differentiate the outside and then differentiate inside. So we already differentiate outside. Now we need to differentiate inside. So differentiating the inside will be df of x divided by dx. So on the right side, when you perform implicit differentiation, you just need to differentiate with respect to x. In this case, that is 1. Therefore, if you want to find the differentiation of the inverse, that will be the same as 1 divided by the differentiation of the original function. So over here, I already excluded the argument inside your function. Okay, so we can test this particular idea by finding this. So we know that this is the inverse function of y equals to ex. So instead of finding the differentiation by first principle of ln x, we can make use of y equals to ex because we already know the derivation of y equals to ex, and find out what is the derivation of y equals to ln x. So from the formula above, this is given by the differentiation of the inverse is given by 1 over the differentiation of the original function, which is ex, because differentiation of ex gives you ex. So we also know that when y equals to ex, then what we can write is this is equals to 1 over y, because y equals to ex. So lastly, we just rewrite the equation. The differentiation of, so we rewrite the equation as in we change back the x and y. The differentiation of ln x will be just equals to 1 over x. So that's how you get the differentiation of y equals to ln x. So if you require second derivatives, basically you just differentiate it 2 times. So let's summarize. When you have x to the power of n, you differentiate it, the index move in front, and then the index minus 1. When it is sine x, differentiate it, you get cos x. When it is cos x, differentiate it, you get minus sine x. Remember how to do product rule: differentiate the first part, keeping the second part, plus differentiating the second part, keeping the first part. Chain rule is differentiating outside and then differentiate inside. And then quotient rule will be to keeping the denominator, differentiating the numerator, minus keeping the numerator, differentiating the denominator, and then divide by the denominator square. Then tangent x, when you differentiate it, you get 1 over cos square x. For y equals to ex, when you differentiate it, you get back ex. If it is ln x, you differentiate it, you get 1 over x. So out of all the functions, the only one that you need to know how to do first principle is the first one, x to the power of n. How to do first principle to get the differentiation, where n is some numbers. So that's all for this particular video. So for the next video, we will look at the first application of differentiation, which is on how you would look at the graph and then analyze the shape of graph and so on. Alright, thank you. See you.